Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. Good morning, Bapak dan Ibu, ladies and gentlemen. Welcome to the second session of already short course, predictive analytics and big data. And I'd like to welcome as well our viewers in YouTube Ready channel. And today we will back again with Professor Ben Feng. And I would like to reiterate the information for all participants today that you are required to follow all the fourth session. And the bonus is we are still organizing or still managing the fifth session, the big data application in industry, especially in Indonesian context. We are still looking for the instructor for that. And also, as you might know that in every session, you are required to at least 70 minutes your participation in the Zoom meeting. And also, at the end of the session, we will inform you that you are required to register again to every coming sessions, like a registration as usual. That's enable us to get your attendance list. Yeah, and also for yesterday, the previous session, the first session, we have a very smooth yet very active participation, and for the question and answer, we still use we are still using the slido.com with the passcode tanda pagar SC16. Jadi kita please access your slido.com with the tanda pagar SC and SC16. That's our code for the slido.com. So with this, the good thing with using another application for question and answer, we are able to focus on the presentation and the discussion rather than rather than having disturbance from pop-ups, question and answer and everything. I think using another application is much easier for us to keep focus on the session. So that's the introduction for the second session. Again, welcome to you everyone, Bapak dan Ibu, to the second session of the predictive analytics and big data workshop. And I would like to welcome Pak.Ben. Pak.Ben, hopefully everything okay with you? And
yeah, good to go.
Okay, so now time is yours. Thank you.
Thank you. Thank you very much for the introduction. Can I have a thumb up? Can everybody see what I share? Okay. So
that's okay. Yeah.
Thank you. So thanks everyone. Thanks for coming back to the second session again. Let's have fun. So today I'm going to continue with where I left off last time. Specifically, in the first session, it was basically a very, very high level and general introduction, just to clarify some of the terminology that's floating around when you talk to almost everyone around you nowadays, like machine learning, statistical learning, predictive analytics. So kind of give you an overview about what each of these terms means. They are similar, of course. In some contexts, they are used, in some conversation, they might be used interchangeably, but hopefully with the presentation last time, you are also clear about some of the distinction among them as well when these distinctions become important. And today, I'm going to be more focused on a specific class of problem, and in fact, one specific algorithm within that class of problems. Specifically, I'm going to talk about logistic regression. And this is one of, if not the most popular and commonly known classification algorithm. So let's just remind ourselves where we are from the big level, from the high level to a lower level. Classification problem is one of the two main categories in supervised learning, which is one of the two categories in deep learning and machine learning. Supervised learning means you have some predictor or some regressor, if you will, X. And X is the feature, Y is the label. Label is what is associated with each of the features. And at the end of the day, a regression problem is trying to predict Y from some X. And in here, I use the notation X star and Y star just to mean this particular X may or may not have been seen in the data set. So sometimes we may make predictions on some of the X that we have not seen before. Okay? But in the data set, we have both X and Y. And this is the common setting in supervised learning. And this can be further divided into regression and classification problems. And the distinction really is in the type of variable in Y, the label. Regression covers situations where Y is a continuous or numerical variable. And for example, I'm giving two examples of regression task, predicting the value of S&P 500 in 6 months. So stock prices are usually continuous, even though we truncate it in a penny. But in any prediction task, we treat that variable as a continuous variable. Or predicting house price based on the location, the year built, or number of bedrooms and bathrooms, and what have you, right? So the house price is Y, the label that we try to predict, and location, year built, bedrooms and bathrooms, and so on, those could fall into the feature, okay? So in the prediction task, in a regression problem, the output is a continuous variable, a numeric variable. In contrast, classification covers situations where Y is discrete. And by discrete, I don't really mean just integers. Sometimes it could be just categorical. For example, male, female, smoker, non-smoker. So there's not necessarily an ordering among the discrete variables. So here are two examples of classification problems. You might want to classify up and down for the S&P 500 in 6 months. Or when you receive an email, you might want to develop a classification algorithm to tell whether a specific email is a spam or not. In the second case, the feature set could be particular keywords. For example, Western Union, for example, just hello to all or to whom it may concern. Some of these phrases or keywords could flag an email whether it's a spam or not. And today we're going to focus on the classification problems. And to make the presentation a little bit more concrete and more specific, throughout the presentation, I'm going to use a default dataset, a credit card default dataset. And this dataset is actually not built in R, but inside one of the R library. I've already, before the lecture, I've sent out the R code that I use to produce almost all the plots and data and the illustrations in today's lecture. So just a gentle introduction of what a classification really is and some of the terminologies. A classifier is nothing more than just a function. It's a function p of x that takes some feature x and predict the corresponding y in some classes. Again, this sounds very much like a regression problem, but the only distinction is that y is a discrete variable. Sometimes are just labels with no particular ordering. And the task at the end of the day is to identify a particular x as belonging to one of many classes. Sometimes we are more interested in estimating the probability that x belongs to each class, rather than definitely saying x must be in class 1 or class 2. Some models, specifically the model we're going to talk about today, predict the probability of x belonging to each of the class, and it's up to the user to develop a decision rule to finally provide a final decision. And this estimate is quite useful in context and in application. For example, it's quite useful to estimate the probability that an insurance claim is fraudulent or not, right? This is a prediction. That means a fraud has not happened yet, but you might want to predict what is the probability that a particular claim is fraudulent or not. Some classification methods first predict the probability belonging to each class and then make the classification as a second stage. And that is definitely the case for today for logistic regression. The first step is just pretty much like a regression problem. Even though each of the class or the label for each of the classes is a discrete variable, the probability for x to belong to each class is actually a continuous variable. So the first step of predicting probability is just a regression problem, and that's why logistic regression is actually called a regression algorithm. The second step would be different for different users and for different applications, but basically the second step makes a prediction to say what is the class x belongs to. And the most common rule is to predict the most likely class among all the classes given the probability of belonging to each class. Okay. So FinTech application, I'm going to use a credit card default dataset, and this dataset has the following columns. Okay, so we have a dataset of 10,000 individuals. Each individual has 4 values associated with him or her. Each individual has a balance which shows the total credit card balance for that individual, and gross annual income for each individual, as well as an indicator variable of that indicates whether a user is a student or not. And last but not least, the label, which is the prediction that we want to make, is whether this person will default on the credit card payment. And that is a label of 0 if no default, or 1 there is a default. The dataset includes the above predictors and binary default labels for 10,000 individuals. So you could imagine in your mind a matrix with 4 columns, balance, income, student, and Y, and 10,000 rows. Each row has 4 columns. Okay, so this is not going to be important until the very end of today's presentation, the overall default rate in the dataset. So out of 10,000 individuals in the dataset, only about 300 people actually defaulted in the past. The precise number is 333. Okay, so keep this number in mind. In your mind, you should think about, well, this data set is very much imbalanced. A lot of them, 99.7% of the label is no default, and only 3% of the label actually has default, as shown in the picture on the right here. Okay, so then whenever you are given a data set, or whenever somebody else gave you a data set, you might want to run some preliminary analysis and see, well, what kind of interesting pattern you might be able to see from just plotting the data. And this is one of them. I'm just plotting the balance on the x-axis, income on the y, and then different marker type on the plot and different color on the plot, just to show you whether a person defaulted or not. Some preliminary analysis. So what I'm plotting here is 2 box plots. Each one has 2 boxes. Okay, and then I'm using the same color as the last slide, where yes is kind of bluish and no default is kind of red. The y-axis shows whether I'm plotting default against balance, or I'm plotting default against income. So let's make a couple of observations just from this simple box plot, right? Kind of standard in any kind of statistical analysis. Defaulted users, so users with a yes, defaulted users tend to have higher balance in their credit card than those who did not default. Okay, so this is by comparing the 2 box plots, specifically the mean and upper and higher percentile. The difference in income levels is less obvious, again, just by comparing the 2 boxes on the right. And to revisit what we're trying to do here, we want to build a model that predicts default or no default for given balance and or different incomes, and as well as the student status. We're going to deal with that a little later. And in this case, default versus no default, these are just 2 different classes, right? There's no inherent ordering or something. It's not even a numerical label. So why is not quantitative? Linear regression is not appropriate. Although you could force yourself to run a linear regression, and this is how, right? You should not do this, but let me just try to give you a reason why you shouldn't do this by doing it for you, right? So why not use a linear regression? The value of a probability of default given balance, or I use p-balance as just to show this probability as a function of the balance, is ranging between 0 and 1, right? So for any given value of income, a prediction can be made for default based on this probability. For example, we might predict default equal to yes for any individual with a prediction that's greater than 0.5, or in fact, the probability of default given a balance is greater than 50%. Okay, and suppose in the data set, inside the data set, the label is either yes or no, and they're in string, right? But you could easily change the label from yes and no to strings to 0 and 1, or the other way around. When you have a default, you label 1. When you don't have a default, you label 0. So then you artificially or purposefully change the labeling, change the label y from non-numeric value into numeric value, right? You change them from yes and no into 0 and 1. And once you do that, you could pretend, you shouldn't do that, but you could pretend that you're just doing a regression problem, because your label now becomes 0 and 1. You just pretend they are numbers. Okay? So if you just pretend they are numbers, again, you shouldn't do it. But if you just pretend they are, you could run a linear regression with no problem, right? So in this case, I make things a little simpler. Y is between 0 and 1. Y is either 0 or 1, depending on whether an individual defaulted or not. X is the balance, the credit card balance of that individual. So I could do this. Let me just warn you, you shouldn't do this. I'm just showing you a wrong example, right? So you could fit a regression line. On the x-axis, you have all the credit card balances, and on the y-axis, you have the probability of default. Okay, so in the data set, you see 2 lines, what kind of lines, by plotting all the people who defaulted in the past are in the upper line where y equals to 1, right? Because they all defaulted in the past, then their label equals to 1. You also have 99.7% of the data set at the bottom with a y value of 0. These are the people who did not default in the past, so their y value, the label for these people, would be 0. Okay, and then there's nothing wrong of running a linear regression, and the linear regression line is plotted in the picture. Okay, it's kind of low, right? It's because 99.7 of the data point are in the 0 level. And that is why the line of best fit actually crosses the 0, but doesn't cross 1, at least within the range that we are looking at here. Okay, so then what's wrong with this? It's a little hard to interpret the prediction as probability now. Okay, so again, the probability of default is on the y-axis. Okay, so somewhere around this point, somewhere around balance equals to 500, that is where the blue line crossed 0, like the blue line becomes less than 0. That would mean, like, if we really force ourselves to interpret what that is saying we predict a negative probability of default. And that is absurd because probability, if we really want to interpret something as probability, then that something is better somewhere between 0 and 1, right? So in the picture, we already see there's a point somewhere around 500, balance in the credit card account. Once the credit card balance is below 500, negative probability prediction. That is absurd. On the right, this is a linear regression line, right? So you could indefinitely extend or extrapolate this linear regression line. So somewhere far on the right, that's not in this plot, there will be a balance level, there will be a value of balance beyond which the probability prediction will be greater than 1. Again, that is very absurd. Okay, so it doesn't fit. It's not unique. This is not a unique problem to this credit default data. Whenever you're feeding a linear regression line, this line could be extended both to the left or to the right, or infinitely extended in any kind of high dimensional space. So there will be, and definitely will be, some points or some area in the space you're looking at where your prediction is outside 0 and 1, or outside 0 or outside 1. And that's terrible because the regression is trying to predict a probability. Any prediction that's lower than 0 or greater than 1 is just absurd. Okay, it doesn't make sense. So now the problem is there any way to change this? Is there any other model that could give us prediction that always lies between 0 and 1? The answer is yes. That's okay. The answer is yes, and the answer is logistic regression. Okay, so let me just clarify. I make it sound like logistic regression is the only answer to the problem. No, it's not. There are plenty of other models that can do this. Logistic regression is probably one of the first model that everybody learns and makes a lot of sense and easy to implement and easy to present. Okay. So to avoid the problem of having prediction outside the range of 0 and 1, we want to model the conditional probability by a function that has a range between 0 and 1. And it just so happened that the logistic function, as I show in the slide, the logistic function happens to have this feature. Okay, so the logistic regression models the models the conditional probability by P of X, where P of X is on the slide. Okay, so if you stare at this formula long enough, you might be able to see the exponent looks like a linear regression. Okay, you're not wrong. That's a correct observation. Let me slowly explain to you what's the similarity between logistic regression and a linear regression, right? Logistic regression on default data is still the same data. We're going to use the same data throughout today's lecture. The logistic function produces an S shape, right? It doesn't exactly look like an S, but everybody says this is an S-shaped prediction, okay? So we always obtain a sensible prediction because logistic regression always gives you value somewhere between 0 and 1, okay? And the prediction can always be interpreted as probability, somewhere between 0 and 1. For extremely low balances, okay, so for extremely low balances, the predicted probability is close to 0, but can never below 0. And for even extremely high balances, the predicted default probability is close to, but never above 1. Okay, it doesn't matter how low the balance is or how extremely high the balance is. The prediction is always between 0 and 1. Then, well, it seems to be a good choice. Logistic regression seems to be a good choice. How do we estimate the parameters? Kind of similar question for linear regression. When we have linear regression models, how do we fit the model? Okay. So this is a one-page explanation about what a generalized linear model is. And definitely, if I expand this, it's going to be another course. Let me just try my best to help building the connection between a logistic regression and a linear regression and try to explain to you what a generalized linear regression is, generalized linear model is. The logistic regression model can be rearranged, right? So Px equals to a strange formula, but it could be rearranged so that P of X divided by 1 minus P of X, the two P's are supposed to be the same thing. So the ratio of P and 1 minus P equals to the exponential of B0 plus B1 times X, okay? And there's a special name for this. This particular ratio is called the odds, which can take value between 0 and infinity. It's an exponential function, so definitely the value will be 0, somewhere between 0 and infinity. And if I take the natural log on both sides, then we get log of this ratio equals to a linear function. And this log quantity, the log of Px divided by 1 minus x, is called the log odds, or an easier pronounced term is called a logit, okay? And logit is linear in X. And this is a generalized linear model in the sense that after some transformation, whether the transformation is linear or not, after some transformation, you could still find a linear model. Then this is called the generalized linear model. Again, this is a very vague and high-level explanation of what a generalized linear model is without explaining too deep into the statistical analysis behind. And I will also comment that GLM, or generalized linear model, is well known and very, very popular in insurance company. Believe it or not, I've known a couple of friends out of undergraduate. The interview question for all of them involve some kind of generalized linear model. Okay, so generalized linear model is arguably one of the most popular and common model in insurance company, particularly for non-life insurance. So let's put them side by side, logistic regression versus linear regression. So I'm putting the math at the top, but don't pay attention to the math, right? This course is not about theory, but just give you the general idea and the intuitive understanding between the two. Okay, let's pay attention to the right first, because that's something we're kind of more familiar with. Linear regression says there's a linear relationship between the regressor and the response. This means increasing x by 1 unit means the probability will be increased by beta 1. That is the slope of the regression line. Okay, being the slope means this is per unit change of y, per unit change of x. Okay, so this probability, because of this constant beta 1, there will be a chance, or there will be an area in which the probability may be outside of the 0, 1, the usual valid interval for probability. Logistic regression, let's turn our attention on the left. Logistic regression, it's kind of a linear model. When you take the log and take the ratio, you have to stare at this model long enough to understand the following. Increasing x by 1 unit changed the log odds by beta 1, right? It changed the logit by beta 1. Yes, something is constantly changing, and something can be somewhere between negative and positive infinity. Okay, but when we backtrack, right, when we change this linear function by taking exponent and by dividing it by 1 plus e to the power of beta 0 plus beta 1x, it multiplies the odds by e to the power of beta 1. And by doing this, somewhat magical, but it's not totally magical, it's more mathematical. After doing this mathematical transformation, the probability is always kept between 0 and 1. Okay. So let me try to dig a little bit deeper into the parameter, especially beta 0 and beta 1, since I'm already on it. Beta 1 does not correspond to the change in the probability directly. Okay. Beta 1, the amount of change in the probability due to 1 unit change of x will depend on where x is, right? It depends on the location of x. If you look at the plot in the bottom right here, depending on where you are in your balance, depending on where your credit card balance is, the slope at that point on the line will be different. For example, if your balance is extremely low, like close to 0, increasing your balance by $10 isn't going to change the default probability by a lot. But if your balance is somewhere between 2,000, if somewhere around 2,000, then changing the balance by a little bit might change the predicted default probability by a lot. Nonetheless, even though it's not a linear change, a positive beta 1 will mean increasing x associates with increasing the default probability. And the reverse is true when beta 1 is negative. A special case I haven't touched in the third bullet point, when beta 1 equals to 0, then the interpretation is more or less the same as the linear regression case. When beta 1 equals to 0, then there's no relationship between p of x and x. Okay, there's no relationship between the feature and the label, and that's kind of rare. Okay, nonetheless, similar to linear regression, whenever we run the logistic regression, we want to do a hypothesis testing to check whether beta 1 is significant or not, and whether we can reject the null hypothesis that beta 1 equal to 0. Okay. So back to estimation again. How do we estimate beta 1 and beta 0? beta 0 and beta 1 in this logistic regression model are unknown and need to be estimated. Okay, same thing in linear regression. Maximum likelihood estimation is popular, intuitive, and has nice properties. So whenever possible, MLE is always the preferred method, if we can, right? So we can estimate beta 0 and beta 1 such that the resulting default probability is close to 1 for individuals who defaulted in the past, and close to 0 for individuals who did not, there's a typo there, who did not default in the past. Okay. So this is the general idea, right? I'm going to show you a formula next, but with the amount of time we have, you don't have to memorize the formula, and there's no point doing that. I just want to show you that, yes, there is a way of formulating this estimation problem into maximum likelihood ratio estimate. Okay, so we can formalize this argument, the MLE intuition, into a log likelihood function. And this huge product will make sense when you realize that we use yi equal to 1 when there's a default and yi equals to 0 when there's no default. Okay, it looks like we have to separate the likelihood into two parts. One part for the observation with defaults and the other part without. But there's a very clever trick of making them into one single product, just depending on the value of the label. Okay, and this can be done. I'm going to show you in the code in a minute. This can be done easily in R. There is a built-in function in R that can just fit the model for you. Okay, so you don't need to memorize any formula per se. What you need to be able to do is whenever you want to do logistic regression, you know how to do it. Okay, as I said in the first lecture, I want to give you hands-on skills to solve problems, right? So I'm going to show you the code after I'm done with the presentation. Are the coefficients significant? Hopefully, with the table here, if you know how to read off the table, if you understand the p-value concept, then the answer is immediate. So let me just go through them anyway with the number in the table. A 1 unit increase in balance is associated with an increase in the log odds of default by 0.055, which is the value for the estimated slope coefficient, or in the table is the coefficient for balance. Okay, it seems small, right? 0.0055, right? Is this statistically significant though, right? The magnitude of a coefficient does not immediately tell that coefficient can be 0 statistically. So what we do, we run a hypothesis testing, right? The heavy lifting, the heavy machinery has already been done. The p-value has already been calculated for you. So a large, in absolute value, a large Z statistic indicates evidence, and very, very strong evidence against the null hypothesis, and the null hypothesis says beta 1 equal to 0. What does this mean, right? It doesn't mean definitely something is true or not. It just means based on the data that I observed so far, and based on the model that I choose, this coefficient 0.0055 is extremely unlikely to actually be 0. Okay, that means this 0.0055 is statistically significant. The estimated intercept, right, the intercept coefficient negative 10.6513 is typically not of interest. It's just a scaling factor that adjusts the average fitting probability to the proportion of ones in the data set. So it's kind of a scaling factor. In practice, we usually don't give any kind of interpretation to it. So with the model already chosen and fitted to the data, how do we make prediction? Shouldn't be a surprise if you have already learned linear regression. After estimation, we can just compute the probability of default of any given credit card balance, even if the balance is have not been seen before. For any individual with 1,000 credit card balance, all we have to do is to plug in that 1,000 in the slope after beta 1. Okay, in the previous slide, beta 0 is negative 10.6513, beta 1 is 0.0055. So the only prediction, the only thing you need to change is this x coefficient or x value, in this case 1,000. Well, here's a typo. When you have a 2,000 credit card balance, not 1,000, we have 2,000, the predicted probability increased significantly from just 0.576 to 58.6%. So it's a huge increase, right? 100 times increase in the probability of default. Again, this is a predicted value. It doesn't say you have to default or not. It's just predicting the probability of default. Then you, as the user or the builder of the model, have to set up a rule, right? So far, what we have done is a regression problem. Okay, so the prediction, as you can see on the slide, the predictions are just numeric values. Okay, it doesn't tell you yes or no. It doesn't tell you whether a person defaulted or not. If at some point, if the output of analysis is required to give a yes and no answer, then you have to make up your mind about what to predict. Meaning in this case, you have to set yourself a cutoff line for predicting default. Okay, whether it's 50%, 25%, or 75%, what have you. Okay, so for example, I'm just giving you an example here. You could classify as yes if the predicted probability of default is 50%. Usually that's a sensible choice, but again, this choice would depend on the problem you're working on. For example, if in some cases, especially for credit card companies, if you predicted some customer will not default, but defaulting has a huge consequence, then you probably want to have some safeguard, right? You probably don't want to have a lot of false positives. So in that case, you probably don't want a 50%. You want to change that to a different number. Okay, 50% is a common choice, but again, that choice could be changed. And qualitative predictor, remember in the data set, there are 4 columns, right? The first column is balance. We use that so far. The second column is income. We haven't used that so far. And the third column is indicator, whether a student is, whether an individual is a student or not. Okay. Inside the data set, it's not an indicator variable. It's actually a string, right? Saying yes or no, whether a student is a student or not, right? So we can, nonetheless, run a regression using a qualitative predictor, using student in particular as a predictor, right? So in this case, we just label student equals to 1, non-student equal to 0, or R will do that for you implicitly. So it doesn't have to do this translation yourself. So when you run R realize it's a qualitative predictor and it assigns a coefficient to that. Okay, what I want you to pay attention to is this coefficient is positive, meaning a student overall will have higher probability of default than non-students do. All right, so we can, based on the estimated coefficients for the intercept and for student, we can calculate that if an individual is a student, then the overall probability of default will be 4.31%. And if an individual is not a student, that default probability is lower than 3%. Okay, so the lesson learned here, when an individual is a student, then this individual is more likely to default, overall at least. So keep that in mind and let me try something else, right? When you're in your statistics class and the first time you learn linear regression, probably by the final exam of the same class, you would have learned something called multiple linear regression. Okay, all you have to do is to have, instead of having one X, you have multiple of them. Okay, it's not a huge extension, but incredibly powerful, right? So the same thing happens here. Rather than having a simple single linear regression, we can fit a multiple logistic regression. We can fit a multiple logistic regression here. And again, the only thing that's changed is how many X that could fit into your model. Rather than just one of them, now I have P of them, right? So without going too deep into the math, let me just run R with multiple regressors. And here I'm going to use balance, income, and student all at the same time and build a multiple logistic regression. Let's check whether these coefficients are significant. P-value, by checking p-values. Balance, extremely significant. The Z statistics is huge, right? Income, not so much. The p-value is about 70%. Some rule of thumb says if this number is greater than 0.05, forget about it. It's not significant. Student, depending on what rule that you use, in this case, suppose we say we use the 5% rule, then yes, student is still significant, right? So conclusion for significance, balance is significant, income is not, student, yes, right? Student is significant. Something I want you to pay attention to, however, is not whether these are significant. Pay attention to the coefficient for student, right? I hope you still remember in the previous page, that number was positive. Well, somehow here with the same exact data, just different number of regressor, the coefficient changed sign. It changes from positive to negative. What happened, right? So this is the right time to introduce something called confounding effect. Probably you have seen that in linear regression, but let's see this again from a real example that we're working on now. This is an apparent paradox. I'm just putting two logistic regression on the slide for you to see. Okay, so I did not change any of the student value. I did not change anything in the data. I just changed what regressor goes into the logistic regression. In a single logistic regression, the student coefficient is positive, and in fact, it's quite positive, 0.4. Overall, students are more likely to default than non-students. Okay, so that's what that positive coefficient says. It says a student is more likely to default than a non-student. But on the other hand, in a multiple logistic regression, the student coefficient is negative. And if we really have to interpret what that means, it says students are less likely to default than non-students. This is clearly a contradiction. Which one is true, right? Suppose all the math is correct and R didn't make any mistake, the coefficients are estimated correctly. What really happened? Because we clearly have a contradiction here. How do we reconcile this apparent paradox? It all has to do with the following. Okay, so on the left, in the picture, I'm plotting the balance. On the y-axis, I'm plotting the probability of default. essentially what I have done on the left is I ran two separate logistic regression. Okay, you see two lines, one in red and the other one in blue. I ran two logistic regressions, one for only the students and the other one only for non-students, right? So on the left, we can see for a given particular balance amount, student is less likely to default than non-student, right? You have to fix a particular balance, right? For a particular credit card balance, a student is less likely to default. However, here's the trick here, pay attention, right? The problem is students tend to have higher balances, right? I hope that makes sense. Students in North America, at least, students would take out student loans, and some of those student loans would come from credit cards. So students will have higher balances, or at least they owe more money than non-students in general, and that's what is showing up on the box plots, right? So then, now what? What does this tell us? Okay, so we have three factors happening at the same time. Firstly, when you have high balance, you would have higher probability of default. Secondly, when you are a student, you would tend to have higher balances. Okay, but nonetheless, when you are comparing two individuals with the same balances, the student is less likely to default than non-student. Okay, so it all has to do with whether you're looking at all students all over, or you are looking at students with the same default or with the same balance. Okay, let me clarify what I mean with bullet points. Holding balance and income constant, right? In the multiple regression model, holding balance and income a constant, a student is less likely to default than a non-student, right? The crucial condition is you have to hold balance and income constant. And as indicated by the negative student coefficient in the multiple logistic regression, that is the case. When you hold those two constant, student is less likely to default. But when you don't, right? Suppose you just close your eyes, ignore the balance and income, averaging over all balances and all income, overall students are more likely to default. And this is the interpretation from the positive student coefficient in the single logistic regression. The explanation is the following. The variables student and balance are correlated. The student population, right, as a whole, the student population tend to hold higher debt, which is associated with higher probability of default, right? So this is the explanation why. The explanation comes from a correlation between student and balances. When you're a student, you tend to have higher balance. And that overall increase the probability of default because of the high balance, not necessarily because you are a student. What does this have to do with the credit card company, right? So yeah, we have identified a statistical problem, confounding effect. Then what's the practical importance? Well, the practical importance is there is a danger of using a single regression when there are other predictors that may also be relevant, right? In this particular case, it's a terrible idea to use student as the only regressor, as we did in the second example, right? It's a terrible idea because you also have balance as a very good predictor. Okay, so the result with one predictor may be quite different than that with multiple predictors, as we see already. When you have multiple predictors, the coefficients can even change signs, right? So this paradoxical phenomenon we saw just now is known as the confounding effect. Multiple logistic regression, or in general, a model with more regressor tend to tease out this confounding effect because With multiple linear regression, the coefficients are kind of conditional, right? The conditional for student, for example, is conditioning on fixed values for income and balance. So practical impact, a student with a given balance is less likely to default than a non-student with the same balance. If you are a credit card company trying to issue credit cards to different individuals, you might want to consider student, right? Yeah, they hold higher balances, but with the same balance as a non-student, a student is less likely to default. Okay. However, if you're only thinking about student population as a whole, they tend to have higher balances. So overall, students tend to default at higher rate. And for a credit card company, they need to try to determine whom to offer credit cards. Then you might want to have a deeper understanding of your applicant than just knowing that this applicant is a student. Okay, so you might want to have somewhat an estimate about what is the typical balance this student might hold before offering a credit card. Okay. So I have built three logistic regressions by now, and let's consider the last example. At the end of the day, we have built a regression model. We say, let's for now say we use the 50% as the cutoff of predicting yes and no. And we want to ask the following question. Is the model any good, right? At the end of the day, what's the point of building a model if it's not for prediction, okay? So we want to know how good our model is, and let's look at the results. A typical metrics or typical way of looking at the result of a classification algorithm is the confusion matrix. The confusion matrix is basically count how many of your prediction is correct and how many of them are wrong. And this confusion matrix I'm showing here is only for binary classification, but when you have more than two classes, the idea is the same. So let's try to read the blue confusion matrix. It's a generic confusion matrix for binary classification. If the actual label, right, if a person actually defaulted in the past and your model predicted that this person would default, then that would be a true positive. Okay, so you predicted a positive and it's actually a positive, so it's a true positive. But if your model predict somebody will default, but this person actually didn't default in the past, well, you predicted a positive, but it's a false positive because in actuality, this person didn't default, right? So the same idea for no. If you predicted something is negative, and in actuality, that person actually defaulted in the past, then that's a false negative. And if you predicted something is negative and in the past that person did not default, yeah, that's a true negative. Okay, you might have heard of this true positive, false positive a lot in the last year when there is testing for whether a person has coronavirus or not, right? So this is what they mean, false positive or true positive. So then we can know a lot from just this table, right? So I use TP, FN, TN, TN, FP, FN to denote all the different shorthands, right? So in the pink or pinkish table, I just fill in the confusion matrix with the number for our multiple logistic regression, right? That seems to be the most accurate logistic regression model we have built so far, right? So I'm just filling in all the numbers. And just to illustrate a couple of metrics that people commonly use to tell if a classification algorithm is good or not. Okay, the first one is called accuracy, and error rate is just 1 minus that. Okay, accuracy means what is the total proportion of your correct prediction. Okay, out of all the predictions that you make, how many of them are correct? Okay, so the numerator is the sum of the true positive, the ones that you predicted positive and actually positive, plus true negative, meaning you predicted no default and the person did not default. Okay, you sum up all the true positive and all the true negative divided by all the prediction. Okay, so that is the true prediction divided by all prediction, and the ratio is called the accuracy. Right? Makes sense, right? In this case, 97.32. Okay, and the error rate is just 1 minus that. Easy to understand what that means. However, there's a problem. Remember, there is a very small percentage, about 3.33% of people who actually defaulted. So in the data set is highly imbalanced. Okay, majority of the individuals did not default, and very small number of them actually did. Okay, so here's an example. The minority class has very, very minimum effect. Okay, so if you have a terrible predictor, in this case, if you just predict everybody defaults, you'll be correct on all the people who actually defaulted, and will be incorrect for the people who did default. And there are only 3.33% of people who defaulted. So your error rate would be 3.33. Well, not too different from the logistic regression. So even a dummy predictor can have a pretty good accuracy. Doesn't feel right, does it? Okay, so just looking at accuracy and error rate doesn't seem to be a right way of looking at this, especially when your data set is imbalanced. So what can we do? There's something else that we could do. Okay, so in our case, default is actually the positive case, right? So default is the minority class if you wanted to. Okay, so in this case, I can calculate the accuracy for the minority class, and it has a special name called the precision. This is saying among all the predicted positive defaults, how many actually defaulted. Okay? So out of all the predictions for the minority class, how many of those predictions were correct? Well, in this case, only 72%. Doesn't look so good, does it? Okay. Second one is called recall, sometimes called sensitivity. This is saying how many of the actual defaults were predicted correctly. So in this case, rather than summing up all the positive prediction, we're going to sum up all the actual defaults. So we're going to sum up all the actual defaults and then ask the question, well, how many of these actual defaults were predicted correctly? Well, in this case, 31.5%. Terrible. Okay. The last one, it seems both prediction and recall have some insights into how well our logistic regression model predicts the value. And F measure is something that try to combine them in a way that makes sense, right? We don't have time to go deeper into what it actually calculates, but I want to give you an intuition. It's trying to combine the precision and recall. It's actually an average of the two, but instead of a linear average, we're calculating the harmonic average. And in this case, 33.9%. Okay, we want, in the ideal case, if your prediction is perfect, all of these should be 100. But no, our logistic regression in this case is not perfect, and this number shows it is not as good as what we saw in the accuracy, which is over 97%. Okay. So these metrics, these three on this slide, are generally better than just accuracy and error rate. Okay, particularly for imbalanced data, which was the data that we worked with just now. Okay. One last slide before we go to the R code. There's something called ROC. For those of you who work with linear regression or logistic regression before, ROC should not be foreign, right? You should have seen this acronym before at least. What it does is trying to look at what were the steps that we took to make the prediction, okay? As the name suggests, logistic regression is a regression. The 50% decision rule, the 50% cutoff, is not and should not be seen as part of logistic regression. And ROC curve realizes that, okay? So ROC plot is trying to plot the true positive and the false positive. The true positive rate and the false positive rate. And false positive rate, even though I didn't introduce that, it's the true negative divided by true negative plus false positive, okay? And the ROC curve is trying to say, well, let me try to change the cutoff value somewhere between 0 and 1, and let me try to give it a plot to say, well, how many times, what is the best trade-off between making an error or making a good prediction, okay? So every point on the ROC curve corresponds to a single classifier, right? So by that, I mean, on one side, you have your logistic regression model, right? So that part is fixed and that part doesn't change. On the other hand, something is changing on this plot, and the value that is changed is the cutoff value, right? We use 50% as the cutoff in the previous examples, and now we want to change that number from 0 to 1. AUC stands for area under the curve, and specifically in this context, it's the area under the ROC curve. And ideally, when you have an ideal predictor and never makes any mistake, then the area under curve would be 1. And the closer to 1 your AOC is, that means you have a good classifier. Okay, so with that, let me go to the R code. Let me show you the R code I prepared, and then just go through the example, but now explanation with R. So I hope all of you by now able to need the data file that, well, not the data file, but the R file that I spread around. And R Markdown is my favorite. It combines R code with LaTeX as well as plain text. So it's very easy for me to give illustration in class and share my code with students. And this one, logistic regression. This is a default data set. So at first, we explain what that data set is. Cleaning up workspace is a very common convention that everybody does. Before starting any calculation, you don't want any variable that remains in your workspace. That's from a previous R code run. And loading all the necessary library that you might need. Okay, so this is my personal convention. I usually write all the code and then start cleaning it up at the end. And rather having a Excel or CSV file, ISLR, Introduction to Statistical Learning with Application in R. That is the textbook that I recommended in the last lecture. In R, there's an ISLR library. It has all the data set that were used in that book, including the default data set that I used today. ggplot2 is just making fancy graphs. GridExtra is helping me show 2 plots side by side. Tidyverse is a huge package that kind of works for data manipulation, right? And that is because ggplot only takes certain data format that may or may not exist in your original dataset format. So visualizing data, I'm showing you the code, how I use ggplot to plot the graph that I show you in the slides. And a box plot, you could save 2 different plots in temporary variables. And the GridExtra library allows you to do something like this. Grid.arrange P1 and P2. So I want to plot 2 plots and number of columns equal to 2. So you have 2 plots side by side in 2 columns. And the results looks like this. Linear regression, let me just skip that. I assume all of you know what linear regression is, and just running a linear regression with summary data, right? So I'm going to skip this. This plot is, I show you the code how to do that in ggplot, okay? Single logistic regression looks like this, is the plot that I use. You don't have to know logistic regression, or at least the derivation for it. In R, somebody has made the code work for you. And rather than LM, linear model, in this case, it's GLM, right? So GLM is a superset which includes linear model. There is a input called family. So this is trying to tell the GLM what is the specific length function, or what is the specific model among all the generalized linear model that I want to use. And logistic regression, so remember this if you are making notes, for logistic regression, the family is binomial. And the most commonly used arguments for family, or most commonly used input value for family, is either nothing. If you don't give a family value, then GLM is only going to run linear regression. Okay, so in all my R codes, I rarely just use LM. I always use GLM. And if I want a linear model, I just don't give a family input. But if I want to run a logistic regression, then the family input equals to binomial. So that's the key in running an R code, right? So you could find out the coefficient by taking a summary and then summon the coefficient in that model. Multiple linear regression and confounding effect. I explained that in the slides a lot more clear, but I just want to share the code with you about how I actually make the plot. Again, for logistic regression, family equals to binomial, right? In here, I again make side-by-side plot. I make 2 plots, and then I use a grid.arrange to say I have 2 plots I want to put in the same figure and want to put them side by side in 2 different columns. So you could imagine if you have 4 plots, then you could arrange them in whatever way that you want, right? So the results here, I calculated a couple of values I introduced in the last couple of slides. This is the confusion matrix, and then accuracy, error rate, precision, recall, F measure, as well as specificity. Okay, so all of these are in the code, and I hope by sensible names, confusion matrix with no, no, yes, no, with all of these, hopefully the explanation is clear and the explanation goes hand in hand with the code. ROC curve, Again, you don't have to generate the code from scratch. One convenience feature in R is if somebody else has already done the coding, you don't have to reinvent the wheel, and I don't recommend you do that. Okay. The last part is something I show you now, but only for the purpose of explaining it next time. Okay. So among the few logistic regression models that were built, we built 3 of them, right? One with balance, the other one with student, and then a multiple logistic regression with 3 regressors. Among these, which one is the best? And what does it mean to be best? One sensible answer is the model that has the best predictive power, meaning it makes the most number of correct predictions for unseen data. But we only have one data set. How do we say we have unseen data? How can we tell whether the model works well in unseen data? So I'm not going to go into the codes for now, but let me give you intuition. If you only have one data set, if the data set is big enough, you have the luxury of holding out part of the data and only train on the other part. Okay, so you split the data into 2 parts. The first part is called the training data, meaning you're only going to use this subset of data to train whatever model that you have. Once the training is done, you use the trained model to make prediction on the other set of data, which is called the test data, or sometimes called the validation set. So that is the essential idea, right? You just make up some unseen data by splitting the data that you have. And validation set is one way to do that. Cross-validation is another. So you split the data into multiple chunks, and then somehow you just make training on some chunks, make prediction on the other chunks. Okay, so that is something I'm going to explain next time, right? So let me just quickly summarize with, let me come back to the slides and then we can start the Q&A. So next time is assessing the accuracy of models, right? So yes, you've built a model. If this were a statistics class, right? So in a statistics class, you will be learning about R square, multiple R square, or adjusted R square, or AIC, BIC. All of those are good, right? All of those are good statistical measures, but they are inside the model, meaning if you are going to use any of those model-dependent measures, the first assumption you make is your model is correct. But no model is correct. So the only criterion that you could use is train your model and then apply your model to make prediction on unseen data. In machine learning, we're going to do exactly that. Okay. So here is a list of questions. Hopefully that will lead to our discussion next time. Okay, so with that, I will close today's lecture and then address any question that you may have. Questions? So let's see. What is the difference between logistic regression and Cox-PH regression? I'm not sure. I'm not sure what Cox-PH is. I'm not able to address that. Although I'm going to make a note of that and come back to that next time. It might be an acronym that I haven't seen before. just for my curiosity, why the logistic function is called odds. I'm not sure if there's a reason or sensible reason to that. Statisticians or mathematicians in general are not very creative in making names. So I'm not sure. It seems to be a convention that everybody adopts, and then maybe that's a homework that I should but haven't done. Would it be possible that the result of all matrices inconsistent among them? What do we do if that happens? Brilliant, brilliant. There's a bad news and there's a good news. Yes, it's possible. The bad news is it's quite common that it's not that all matrices will be consistent among them, but it's very, very rare, extremely rare that they all agree. Okay, let me just put it that way. So the good news is it depends on the task that you have, right? Which matrix matters the most to you. Usually, if you know the actual problem well enough, you will kind of have a sense what means the most to you. For example, when just use the pandemic, for example, it's much more costly if you identify a person as negative, but the person is actually positive, right? So if you diagnose someone negative, but the person is actually positive, then you will run a high risk to the society because you are letting out an infected patient into the population, right? So in this case, a false negative is very costly. So you will look at the metrics that focus on minimizing false negative. Okay, so let me just reiterate. It's very common for the different metrics to disagree with each other. The good news is you usually know which one you should use and focus on, right? When we predict the outcome in logistic regression, how to choose the optimal threshold of the probability prediction, which is between 0 and 1 into 0 or 1. I don't think there's one right answer to that. What usually happens is you look at the ROC curve and then pick the one that's comfortable for you. Okay. Again, it kind of ties up to the question just now, which metrics you should look at, because the ROC curve gives you kind of a cost-benefit analysis. So rather than saying which particular value is the best, you have a range of values that you choose from. And then depending on whether you focus on the false positive or false negative, well, when you make false prediction, it depends on which false prediction matters most to you. And then on that, you choose yourself somewhere on the ROC curve. Remember, every single point on the ROC curve corresponds to one value. So you will pick a point that makes you, that makes you comfortable, right? So the ROC curve is the picture that you should look at in order to make this decision. Logistic regression can be used as a tool in reviewing / updating pricing mortality table. Yeah. In your opinion, what is the strength and weaknesses of using it? I have to be honest, I haven't seen this application, but I can see how it can be done. The problem with updating mortality table is how many data points that you have. From my understanding, you don't have that many data points, right? Data points meaning how many different mortality tables that you have. And usually, in the extreme case, you only have one, the most updated one from the last census. So from that viewpoint, I would say the lack of data or the limited amount of data alongside with quantity or alongside with the quality of the data would be the weaknesses of using logistic regression. Strength, well, when it comes to logistic regression, the strength is always simplicity. The model is simple and the interpretation is simple. Right? There's always a trade-off. It's a model with high interpretability but low flexibility. If there are many variables, do you think MLE is good because it needs approximation of a function of many variables, especially not a continuous function? Good point. Good point. Obviously, the student has very good sense about optimization. Based on the way you ask the question, I might say no. But a follow-up question from me is, what's the alternative, right? So if a model has many variables and you want to calibrate all these variables, what else can you do besides MLE, right? You might add regularization so that you have a more sparse model or a model with a smaller number of variables. You could do that. So if you are thinking about the alternative being least square, then yeah, you can do that. But I just wanted to say, when you run a least square, you still have all the variables potentially being non-zero. So I'm not sure whether you actually have a simpler optimization problem. Okay? So when MLA is difficult, in my opinion, the alternative is also quite complicated, right? So by all means, if you have a better alternative, simpler to estimate, simpler to optimize, and also makes sense, by all means, you should do that. Can logistic regression be used to, oh yeah. It depends on your encoding. Yes, definitely you can, and it's constantly being used for that. Can logistic regression used for, I'm not sure I understand what the last two phrases are. Is that a typo or is that actually a problem? I'm not sure. If you could explain a little bit what the last two terms are, I might be able to comment on that. Or instead of typing, you might want to unmute yourself and then explain.
Ya, Ibu Bapak, apakah ada pertanyaan lagi? Is there any more question or discussion that you like to?
Oh yeah, somebody's, oh no.
Yeah.
I think the ready admin is trying to ask the person who asked the question. So here's another one just came up. If we have label as binary ordinal, which one appropriate using ordinal or I thought regularized logistic? If, right, so whenever you have ordinal data, so just at face value, if you're just asking this, then ordinal logistic would be a better choice. But the only thing that I would add to that is when you have ordinal data or ordinal categorical data, check the scale. Okay, so yes, you have order, but does the scale matter to you? Okay, the scale of the data, and then by that, you might also want to check in your label as well as your features when you are measuring. Does the unit of measure matter? Okay, if the only thing that matters is the order and the difference, whether it's between 1 and 2 versus 1 to 200, if the scale doesn't matter and just the order matters, one is bigger than the other, then by all means you should use ordinal logistic.
Okay, no more questions. We have still, yeah, we are just on time there. Yeah. Okay.
That's a rare event.
Yeah, we will invite 1 or 2 more direct discussion rather than through Slido. If Bapak Ibu like to have a discussion with Prof.Ben directly, just raise your hand or you just turn on your microphone. It's fine. Okay, I think if there is no more question and discussion, I think we can conclude to today's session with Prof.Ben, and let's make a big applause to Prof.Ben.
Thank you very much.
Thank
Appreciate
you.
it.
Yeah, thank you,
Thank
Prof.Ben,
you.
for your facilitation.
Thank you very much.
And we will meet again on next
Tuesday.
Wednesday, yeah. Tuesday in Canada and Wednesday in Jakarta time. It's always confusing between us, Prof.Ben. Yes. Yeah. And Ibu Bapak, please re-register again to the link that Ibu Yvonne will provide to you by email. That enable us to record everything based on the entrance registration. And again, thank you, Prof.Ben. Thank you, Bapak Ibu, for your participation, and see you next Wednesday. Dari saya, wassalamualaikum warahmatullahi wabarakatuh. Salam sejahtera and good afternoon, good evening. See you next week. Yeah.
Hey, thank you very much, everyone.
Thank you.
See you next week.
Thank you. Bye-bye.
Thank you. Bye-bye.